All right, mic check. Everything should be good. So, welcome back to CS196 once again. Today we have a lecture on functional programming. So, functional programming is this idea, this very powerful programming paradigm that many of you probably aren't super familiar with, and it's a shame that that's the case because it's very powerful and it's something that once you know, you'll find yourself actually using from time to time. It's something that also isn't really taught in detail until CS421 at this school, and that is like the last class that people take as a CS major. It's usually the class they take in their final semester here. So it's a shame. It's quite powerful, and so today we'll be covering functional programming and how it looks like in Rust. So let's get started. So in our first lecture for Rust, we talked about how Rust is a multi-paradigm language. Now, what does this phrase right here, multi-paradigm, mean? Well, there are different ways of programming, different programming paradigms, and the ones that you are likely most familiar with is object-oriented programming. Java is very much an object-oriented language, and it is very heavy on object-oriented programming. That's the paradigm that you're likely, very comfortable with at the moment. But Rust supports many different paradigms. It does support some object-oriented features, and today we'll be talking about the functional paradigm. There you go. Today we'll talk about functional programming. So what is functional programming? Let's go ahead and get started. So functional programming is the process of building software by composing pure functions, avoiding shared state, mutable data, and side effects. Contrast this with object-oriented programming, where application state is usually shared and co-located with methods in objects. This sounds very long-winded, a little bit complicated, but you should kind of have a general idea of what a lot of this means. For the things that you likely don't know what it means, let's break it down. So we talked about how it composes pure functions, avoids shared state, mutable data, and side effects. So, shared state and mutable data, you should kind of have an idea of what that means, but first let's break down this idea of a pure function. What is a pure function? Not too crazy. It's the idea that every input has the same output. And so the best example of this is a very simple mathematical function where we say, let's define a function f of x is equal to 2x. And if we input 2 into this function, we will always get 4 out of it. And anywhere where we see f of 2, with this function being the one that's defined, we could even replace f of 2 with 4, and the behavior will stay the same. Nothing will change. Now, to contrast that, let's look at the random function. If we had, for example, a random function that took in two parameters, a lower bound and upper bound, and we said, find me a random number between 1 and 4. The output from that function will definitely not always be the same. And if we were to try and replace like f of 1 comma 4 everywhere where we see the output of that function, we cannot guarantee that behavior wouldn't change. So the idea of a pure function is just essentially that every input has the same output. Random functions, of course, are not pure functions. Now let's define some more of these terms. So we talked about side effects. And so side effects are any application state change that is observable outside the function other than its return value. And some examples of this are modifying global variables, console logging, etc. So to break this down even further, a side effect is basically saying that like when you're calling a function in functional programming, you aren't expecting anything other than getting the return value. So from the time that you call the function, from the moment that the parameters are inserted into the function, to the moment that you're getting a return value, you're not expecting things to change outside of this function. You're not expecting to see things being console logged. You're not expecting to see global variables being changed because that's not observable from outside, or that is observable from outside of the function. So we try to avoid these kinds of side effects with functional programming. And so what are the benefits of using functional code? Why is functional programming something that is good to be familiar with? Well, functional code tends to be more concise. It tends to be more predictable. It's easier to test than imperative or object-oriented code. Imperative programming is just another programming paradigm. And if you're unfamiliar with it, this is kind of the issue. and the common patterns associated with it, functional code can seem a lot more dense, and the related literature can be almost impenetrable to newcomers. So in other words, functional programming has a lot of benefits, and it's something that is great to know. However, the ideas in functional programming at first can be a little bit difficult to wrap your mind around because, as you'll see later, some of the concepts are a little bit weird. So let's get started. Our first feature of functional programming, first-class functions. So it sounds very complicated, this phrase first-class functions, but let's break this down. So first-class functions is this idea that functions are essentially treated like any other variable. So for example, in a language that supports first-class functions, a function can be passed around like an argument to other functions, it can be returned by another function, and it can be even assigned as a value to a variable. So this is a little bit of a weird thing to kind of wrap your head around. We're treating functions as if it was like an integer or a string. We can pass it to functions, we can return it from a function, etc. Right? We can assign it to a variable. This is a bit weird, but we'll see why it's useful and how to kind of help yourself wrap your mind around this concept. So first things first, an example of a first-class function. Here's another fancy word coming out at you, a closure. A closure is an example of a first-class function. What is a closure? So closures are what are called anonymous functions that you can save in a variable or pass as arguments to other functions. And so this phrase anonymous function here means that these closures do not have a name. And so we refer to the anonymous function by using the name that is referring to it, but that does not make it a named function. And so this sounds a little bit weird for now, but once you actually get to take a look at a closure, you'll notice what I mean here. So unlike functions, closures can capture values from the scope in which they're defined. Again, all of this will make a little bit more sense with an example. So let's see what closures look like in Rust. And I say in Rust because closures is not a Rust-specific concept. You will see closures in a lot of different languages that support functional paradigms, and you will certainly see them in languages that are, entirely built off of the functional programming paradigm. But let's see closures in Rust. So here is a normal function. We call it add2, and I think you should know pretty obviously what this function does. It takes in a parameter and it adds 2 to it. Don't worry too much about the usefulness of this function, it's just to explain the syntax behind a closure. So let's start off with this example. So how can I convert this normal function here to a closure? So I'll have them side by side. On the left, we'll have the normal function, the function that we're starting with, and then we're going to see how we can take that function and transform it into a closure. So first things first, we said that closures are anonymous functions. What does anonymous function mean? It means that the function doesn't have a name. So simply, we can just take out the name that we saw associated with this function. So now we have these parentheses with the arrow, same thing as what we see on the left, just the name omitted, right? So next step is that in Rust, instead of having these parentheses, we define closures by having these vertical bars. So we'll replace the parentheses with these vertical bars, and so now we have a valid closure. But we can go even further. There are a few things that we don't need in our closure syntax. This is a valid closure, but we can reduce even more. So one way we can reduce is by removing the types. So with closures, unlike functions, Rust can actually assume the types of your variables and your return values. So we can just completely take that out from our closure. But again, I just want to stress, both of these are valid closures. And so now we have just the parameter x in this closure, and it would return x plus 2. Throughout all of these reductions, the behavior has not changed. It does literally the same thing. But even now, we can reduce our syntax even more. So you see these little curly braces here. Since our expression is only one line, since we only have one expression, x plus 2, we can actually take out the curly braces as well and have this entire function transformed into this closure on one line. And so this is our final modification to the syntax. This is what a closure will look like. So let's continue here. I want you guys to notice a few things from the example that we talked about. So we said that to define a closure, we start with a pair of vertical pipes, and inside we specify the parameters to the closure. So that's exactly what you saw here. We have these vertical pipes. This is how we define a closure in Rust rather than a function with the parentheses. And we obviously put in the parameters. So in that case, the parameter was x. If we had more than one parameter, we would separate them with commas, just like a function, nothing too crazy here. And after the parameters, we place curly braces that hold the body of the closure. These are optional if the closure body is a single expression. So in other words, this is just like a function, and we saw exactly that right here. We took out the braces and we left it all on one line because we could, right? And so this is all seen in this example exactly. So let's have our first Kahoot question. Join in with your net ID, just like usual. And we'll give you guys about like 2 minutes or so. So someone asked, can you normally remove the braces in a normal function, given that it's one line? I believe you can. That isn't really specific to closures. What's specific to closures is like everything else you saw. Removing the name of the function, removing the parentheses in place of the vertical pipes. But yeah, you are right. If it's one line, you can remove the curly braces. Everything else still stays the same. Give you guys another like 30 seconds or so. Want to get started here. Looks like the numbers are slowing down, so let's get into it. So 2 questions to start with. I'll move out my camera. So, true or false? First class functions allow you to treat functions like any other variable. Alright, well done. Well done to the 57 of you. This is definitely correct. First class functions allow you to treat functions like any other variable, and an example that we saw of that is a closure, and we'll see how we can kind of treat them as variables in some more examples later on the slide. We'll see them, passed into functions, returned, etc. So let's do one more question for now. So which of these are valid closures? You guys have a little bit more time for this one, since you have to look at it, but should be fairly straightforward. We're almost there. 10 more seconds. There we go. Okay, so there were 3 correct answers here. The only wrong one was yellow, and the reason why that is because if you look carefully here, these are parentheses, and so we said the parentheses in Rust are how you have a function. The vertical pipes is how we have a closure. Why are these right? It's because we said, well, with closures, you can omit the types, but you don't have to. This one is also correct because we said that you can omit the parentheses, but you don't have to. And here we said that you can omit everything, so that includes the types, the curly braces, etc. So this is the example. All of these we saw in the slides, but this is the one that we resulted in. Someone said, does the semicolon after the closing brace not matter? I think I might have just put that in on accident, but what's important is this part. So let's continue. Let me get my camera back in. The important part is the closures. Let's continue. All right, so we talked about how these are anonymous functions, and we said that even though we can assign them to a variable name, that doesn't mean that they are named functions. It means that they are still anonymous, it's just the way that we refer to them is like so. So this closure, we are assigning it to this variable, add closure, and the reason why we can do that is because it's a first class function. And the way that we call this function is by using the name of the variable that we've assigned it to. So if I wanted to call this function with the parameter 2, we would do it just like so. Nothing too crazy. It's just a little bit weird for people at first to see this little line of code right here, where we're literally assigning a function to a variable. So that's the little note we said here. We refer to the anonymous function using the name of the variable that is referring to it, but that does not make it a named function. Let's continue. So this one is a useless closure, and I'm simply having this here to have to prove another point that we talked about in the previous slides, where we said that closures can actually capture the scope of the capture variables within the scope that it is in. So in other words, here we have x that is defined within this scope here. In this function here, I can actually access this variable because of the properties of closures. We can access variables within the scope that it's defined in. So that's this little note here. Unlike functions, closures can capture values from the scope in which they're defined, and we'll see how this is a little bit. We'll see how this is useful later into the lecture. So now that we're done talking about first-class functions, let's see how we can use them in combination with this idea, this new idea in functional programming, new to you at least, higher order functions. So higher order functions, another fancy term, but really all it is that it is a function, any function, which takes a function as an argument and returns a function or both. So a little bit of a mouthful here, but let's see what it looks like. So here's our first example of a higher order function, and this is the map function. So the map function takes a function or a closure and a list, and it applies that function to every element in the list, and it produces a new list. A little bit complicated, but let's see an example. All of this is best taught through an example. So first things first, we have defined a list. Very simple, 1, 2, 3, or we can, it's a vector. And so in our second vector here, we'll see how this operation here produces a new vector. We'll store that in v2. And let's take a look at the syntax here. First, I want to focus your attention to map. So we said that map takes a function or a closure and a list and applies that function to every element in the list. So what does this closure do? Well, this closure by itself, very, very simple. We know that this will take in a value, it'll add 1 to it. That's all it does. And so map will take this function and apply it to every single element of this list. So what we'll see is that we'll apply that function on 1. 1 plus 1 is 2. This value in the list is 2. It'll do the same thing there. It'll add 1 to it. And of course, the same thing with the third element here. So that is what the map function does. And we can see this right here. Map takes a function or a closure in a list and applies that function to every element in the list, producing a new list. And in this case, the output will be 2, 3, and 4. Now, there are two things here that you might not be super familiar with. First things first, you see this .itr here right after the vector. This is how we get what is called an iterator out of the first vector. And so the reason why I say that is, here we said that we can apply it to a list, but we can actually correct that. We can apply it to an iterable. And what that means is, we have many different types of data structures. We don't only have lists. And so an iterable is literally anything that you can iterate through. And so the reason why we have these iterators is because, for a list, it's very simple. The way that we iterate through it is like a for loop, right? But for other data structures, it's not always like super straightforward in how you would traverse it. So iterators are kind of like a wrapping layer over the traversal of a data structure, so you don't really need to worry about it. All you really need to care about is that you will be iterating through the data structure. Examples of this are like a binary tree. There are many different ways that you can traverse a binary tree. You can start at the root, go from left to right. You can start at left nodes and go from the root to the right, etc. Many different ways you can iterate these data structures, but an iterator will just basically abstract all of that away from you, and it'll just say, all right, we're iterating through this. And so in Rust, these higher order functions can be applied on any iteratable, and it will return a new iteratable. And so this collect function on the right side here, what the collect function does in Rust is it'll take one of these iteratables and it'll convert it into a list. And so in this case, what we see is that we have v1, we convert it into an iterator, and we can apply the map function to that. And so we'll, apply the function to every element of the list, and then at the end, collect will collect all of the elements and plop them in a list that looks just like this. So I hope that makes sense, and let's continue. So this little visual here is not Rust, it is actually JavaScript, but that doesn't really matter. It goes to prove the point that functional programming is in more than just Rust. It's in many different languages. So here is a nice little visual on what's going on with the map function. We have our input value and then the transformation that we are performing on the input value. The entire thing here is the function statement, and map will morph the array piece by piece. And so this is the result for this example here. So let's have a Kahoot question. What does the map higher order function do? Okay, so we have a question in the chat that says vec underscore, what type is that? The underscore is basically a type in Rust that's just like a placeholder, essentially saying that you don't really need to worry about it. And especially for this lecture, you really don't need to worry about it. The focus is on the functional aspect of it, but the underscore is just a placeholder. Okay, so well done. You are correct. Map higher order function will take a function or a closure. A function or a closure and apply it to every element in the list. So that is correct. The other ones are not correct. Will it always create a vector no matter what the initial iterable was? I believe so, but you'll have to check the docs on .collect. I believe that is the case though. Okay, so let's learn some more higher order functions. So we talked about the map function. Now we can talk about the filter function. So the filter function is a higher order function that constructs an iterator from elements of an iteratable for which a function returns true. So the important part here is that it will filter out things that don't return true for a certain criteria. So what it allows you to do is kind of define a certain criteria, and beyond the point that you use filter, the things that don't pass that criteria won't proceed forward, if that makes sense. So let me move my camera as well. So I don't want you to get too confused over the iterator and iteratable. If it's too confusing, you can think about it as it constructs a list from elements of a list. An iterator and an iteratable is just our way of abstracting even more, saying that we can do it to things more than just a list. So let's take a look at of how filter can be used and how useful it can be. So let's say that we have, for example, a website where we are providing functionality to kind of search through shoes. And one of these pieces of functionality is to find shoes in your size. And so let's pretend like shoes are stored in this website as as size with an integer and style. So style being just the string of what kind of style shoe it is. And so with shoes in my size, what we can do is focus your attention right here. We can convert the vector of shoes into an iterator and then apply the filter function, the filter higher order function to it. And so the closure that we're passing to it is basically saying that for each shoe, if the if the size of the shoe that we're looking at is equal to the shoe size that we're looking for, then we can allow it to proceed forward. Essentially, it passes this criteria, and we allow it to be output into the new list. And so one thing that I want to note, so yeah, this is something we said here. Filter method constructs an iterator from elements of an iterable for which a method returns true. So in this case, the method that we want to return true is the shoe size that we're looking for being equal to the size of the shoe that we're looking at. And so a very important thing to note that we talked about earlier, we said that unlike functions, closures can capture values from the scope in which they're defined. So here, the scope is this entire function, and we said that closures can capture values from the scope in which they're defined. What is the value that it's capturing? Shoe size. We can still access this variable despite it being inside of the closure. And so someone says, why is it into iter in this case and iter for the map? I believe they should be performing very similar, but I'd have to look into the differences. And someone says, are anonymous functions the same as lambda functions? Yes, if you know what a lambda function is. It depends on the language that you're working in. Some languages call them anonymous functions. Some languages call them lambda functions. They're kind of interchangeable. So let's continue. So we can take a look at how this function that we created is useful, where if we had like this vector of these shoe structs, and we said that one shoe is of size 10 and it's of type sneaker, another shoe is of size 13 and it's of type sandal. What we want is shoes in my size. So let's say your shoe size was size 10. What would happen here is we would convert it into an iterator. And with filter, for each element here, we'll check is the size, so in this case 10, equal to the size that we're looking for, which is also 10. That is true. So we want to preserve this shoe. Let's continue. This shoe right here, size 13, is it equal to 10? No, it's not. So we don't want to output this. And finally, shoe size 10, is this equal? Yes, it is. And so it goes into the output list. And so what we would get from this is the sneaker and the boot. So I hope that makes sense. And here's a little bit of a visual that helps kind of understand a little bit better what filter is. Again, this isn't Rust here, but many languages use these examples. Many languages use these higher order functions. The visual here is that you define a criteria, and the only things that you'll get out are elements in which this criteria returns true. You are quite literally filtering out the elements that don't pass this criteria and only receiving the ones that do. So in this case, you have an array. Any number that isn't less than 10 will not be in the output. So let's have a Kahoot question. Well done to the 52 of you. Filter, it'll make a list or an iterable from elements of a list or an iterable for which a function returns true. Well done. And to answer the question from before, why is it into iter in this case instead of iter for the map? It has nothing to do with filter versus map. Iter is related to like it'll give you essentially the items by reference, and into iter is a little bit different. But the focus isn't there, and I'm pretty sure it would work regardless of which one you use here. So let's cover our last higher order function for today. So another example of a higher order function is the fold function. So fold will, let me bring my camera down. Fold will apply a function to an iterable, producing a single final value. It takes in two arguments, an initial value and a closure with two arguments, one being an accumulator and another one being an element. The closure will return the value that the accumulator should have for the next iteration. And this is similar to the reduce higher order function that are in other languages. So fold is kind of like the name that Rust gives it, but in other languages this is known as reduce. And we'll take a look more specifically at the behavior of fold and kind of break down this little long-winded thing right here. So here we have a list, 1, 2, 3, and so we said that fold takes in two arguments, an initial value and a closure with two arguments, an accumulator and an element. The closure returns true for the accumulator that the accumulator should have for the next iteration. So here is our accumulator, here is our element, and here is our initial value. And so what this closure does here is it'll essentially take the previous value, which is in the accumulator, and this will be initialized to 0, and then it'll add it to our current element, which in this case is x. So for each element, x, we will take a look at the accumulated, in this case, the accumulated sum, and add that to our current value. So let's look at this example here. So we initialize accumulator to 0 because we set that value here, and x will be, in this case, 1. So we start off, we say 1 plus 0 is equal to 1. So we said that this closure will return the value that the accumulator will have for the next iteration. So 1 will be put into this accumulator for the next iteration, and on the next iteration we have value 2 in for x. And so from there we can say that 2 plus 1 is equal to 3. And so this will be output into the new accumulator for the next iteration. And so we'll say that 3 plus our next element, which is 3, is equal to 6. And so this will return 6. And this entire line right here is the sum of all of the elements in the array. And more importantly, we talked about how fold will apply a function to an iterable, producing a single final value. So the single final value in this case is the sum of all of the elements in the array. And the function, of course, is this little closure right here that does exactly that. It has the logic for summing. Someone says, is the filter function like list comprehensions in Python? Kind of similar. There are I think there are some differences, but very, very similar. You have the right idea with that comparison. And someone says, is fold a recursive function? So what essentially any of these higher order functions do is it'll follow the iterator. So not necessarily recursive. You can think of iterators as like a pointer. So in this case we'll initialize our iterator. We'll start our iterator at 1. We'll apply the fold function to that element. We'll apply the closure to that element. Then we'll follow the iterator to 2. Then we'll follow the iterator to 3. Someone says fold seems awfully specific. Why use fold when you can just use a loop? Because today we're talking about functional programming, and also I'll show you a little bit of a better example of like kind of the place in which you would use fold towards the end of the lecture. There are realistic examples of why you would want to use it, and I'll show you that later. So if you're a visual learner, here is a nice little visual of what, in this case, reduce, but like I said, Rust just kind of calls it fold. Reduce, in this case, is what JavaScript and many other languages use. So let's take a look at example here. If we have this this list of ingredients, wine, onion, and mushrooms, and we want to reduce it or fold it into a single output, we can apply that function to the list. And so in this case, we're cooking every single item, and what we'll have is a sauce full of cooked items. And so the example, this is a bit of a goofy example, but to the question that said, like, it seems awfully specific, in that case, I mean, we were just using it to loop through some values, essentially, and accumulate the sum. But when we use these higher order functions in combination with one another, what you'll find is we can produce these very powerful like data processing pipelines. So before we get into that, let's have our Kahoot question, and I can show you a better example of the use cases after this. So what does the fold higher order function do? Okay. So by now, I hope you guys get the point here. So the other examples, so makes a list from an elements of a list for this is filter, this is map, and the one that we're currently looking at is fold. It applies a function to a list, producing a single final value. So let's put it all together here. We can chain these higher order functions together, and the use cases that come out of this are very powerful. So as a testament to how powerful it could be, Google was able to build an entire distributed data processing on top of these higher order functions. Let's look at an example. So their system was called MapReduce, and as we said that in Rust, reduce is actually named fold. But let's take a look at an example here. So here we have this little playground. And our example is, let's say we have kind of like a database of NBA players where each player has their name, the points that they've scored in a given season, and the points that they've assisted others in scoring, and whether or not they're an all-star. And so in our main function here, I just defined a couple of these players. Obviously, if we just pulled in from a database, we'll have much more than it looks like 5 here. But let's pretend like we're sending this data, like very large data, through this pipeline. So here are all of the players that we've created, and we will call our method All-Star Summer on this vector of players. So most importantly here, let's take a look at what's going on in our method here. So All-Star Summer will take the players and we'll put it into an iterator. And first things first, we'll apply filter. So filter will, for each player, essentially filter out any player that is not an all-star, because we said that filter is like kind of like a constraint. It'll have this criteria that you've defined. So in this case, it is whether or not the player is an all-star, and it'll only let through those in which this variable, this expression returns true. So beyond this point, we will only have players that are all-stars. And so in our example, this will give us LeBron James, Joel Embiid, and James Harden. So now we said that we can actually chain these together because every single one of these higher order functions return an iterable. And we said we can apply these higher order functions on iterables. And so as a result, we can chain them together very nicely. So with the map function, we can apply this closure on what filter gave us. So map, our closure will basically go through, in this case, the all-stars, because we are no longer looking at players, we are looking at all-stars here. And for every single all-star, we want to sum together the points that not only they scored, but also the points that they helped other people score. Just because that's what we want our method to do. So for every single all-star, it'll do this. And so from there, that we will get an array of the total contributions for each all-star. And so finally, we can use fold to sum all of the points together that were given to us from map. And so if we run this, we'll see that in this case, we have 5,856. That's just this example, but the important part are these little methods right here. So we talked about how functional programming, like these concepts, allow us to write very concise, beautiful, elegant code. If we imagine what we would have to do if we did this in a different programming paradigm, this would be quite a bit of code. But as a result of using these higher order functions, this functional programming style, it's very easy to follow, it's very elegant, and we can debug this very easily. If something were to go wrong, there isn't much code to look at here. So there are many benefits of using functional programming, and those are just a couple of them. And so you notice this comment here. We said that there are better ways to do this. This is simply an example. I say that there's better ways to do this because we could probably reduce this down to like using one or two of these higher order functions, but I wanted to use all of them so you guys can kind of see how the pipeline would work. Let's go back to the slides. Okay. So I cannot stress this enough. These ideas extend far beyond Rust. You'll find these functional concepts in Java, JavaScript, Python, etc. There are programming languages that are built entirely on the functional paradigm and restrict you to only the functional paradigm. You'll see the languages that are constricted to those paradigms in CS421, for example, with Haskell, OCaml, things like this. But again, extend far beyond the confines of Rust. So with that, it is the end of the lecture. I'll let you guys off on a little bit of a funny tweet. Map filter reduce in a tweet. So we apply the cook function to this array of raw food. We'll get cooked food, and then we'll filter out all the foods that aren't vegetarian. And then from there, we will apply the eat function and reduce it down to what you see here. Have a wonderful Thursday night. We will see you guys next week with concurrency, where we will take these closures and use them for multi-threading. Until then, have a wonderful weekend. And if you have any questions, I will be here.